Hi students, in this clip we are going to discuss about knapsack 01 knapsack using branch and bound. Okay, and here you have an example. So you have some items with weights and values, and the knapsack capacity is 10, and like greedy knapsack we arrange it in order of decreasing value by weight. Okay. um, all right. So you need branching condition. You need a good upper and lower bounds for in order to use branch and bound, right? So how do you calculate these upper and lower bounds? All right. So what we are going to do, branch and bound. We have used it for minimization, right? So because we are using branch and bound as applied to minimization problems, and knapsack aims at maximizing the profit, so we just invert the sign. Okay, we just invert the sign of the profit, and so the maximization problem is converted to a minimization problem. Okay. And so what are the upper and lower bounds for this problem, right? So it's easy. You, from the given problem state, find out maximum profit using greedy knapsack. See, when you use greedy knapsack, it actually tells you the maximum profit you can obtain. You can never outperform greedy knapsack. Okay, so this immediately is like an upper bound, but it can be converted to a lower bound because you are inverting the sign. You are negating it. Okay, so this is regarding your lower bound C cap. It is found by using greedy knapsack, and the upper bound is obtained by simply adding items one after the other until the weight is exhausted, and counting the profit. Okay, so you add items one after the other in the order of the items until the weight is exhausted and find out the profit. This gives you an upper bound. Okay, and you negate it, of course. Okay, this actually, the second one actually is a lower bound, but because you are negating it again, you make it as an upper bound. Okay, so this is basically what you are doing. Now let's go on to this example. So you have four items and you want to use knapsack. Okay, so in every state we have written down what is the weight and value obtained till now, and also below we have written lower bound and upper bound. Okay. Okay, initially W equal to 0 and B equal to 0. W is the weight and B is the value profit. Okay, so when no items are chosen, then what should you do? In order to find out the lower bound, you have to use greedy knapsack. Okay, so maximum knapsack capacity is 10, which means that can be exhausted by using 4 units of the first item and 6 units of the second item. So that would be 40 plus 36, which will give you 76 minus 76. Invert the sign. Okay, and then the upper bound can be obtained by adding items one after the other until the weight is exhausted. If you do that, you will add the first item 4, but you cannot add the second item because it has a weight of 7. Okay, so this upper bound means that you have to add items one after the other entirely, not partial, not fractionally. So you cannot add the second item, right? So you stop there, right? So you get minus 76 comma minus 40. You don't try to add 5 and all that, right? You just add one item one after the other until it's the weight is you know weight is exhausted, right? If the weight, yeah, so you have here minus 76 and minus 40. Okay, from here you consider x1 equal to 1, which means you are including the first item, right? If you include the first item, then w changes to 4 and b changes to 40. Okay, and then let's write down lower bound and upper bound. Like I said, lower bound is found using greedy knapsack, that will remain minus 76. Okay, and the upper bound by adding the items one after the other. Again, you cannot add the next item, so you just simply stop there, right? You say minus 76 comma minus 40. Okay, and then x1 equal to 0. So here what happens, x1 equal to 0 means still w equal to 0, v equal to 0. Okay, so if you exclude x1 equal to 0 means basically exclude the first item, right? Now apply greedy knapsack again, which means that you will include 7 units of second item and 3 units of the third item. So you get 42 plus 15, which is 57, right? So you write here 57. And then by the upper bound, you add this item, but you cannot add the second item because it will exceed the weight constraint. So you stop with 7. So that will give you a profit of minus 42. Okay. So from among these two nodes, we find that minus 76 has the lesser cost. You check the lower bound and you explore the node which has the lower C cap value, right? Because your objective is to minimize. Okay, so you expand this node. First check out for x2 equal to 1. Now x2 equal to 1 means the weight constraint is not satisfied, so it cannot be explored. You check out for x2 equal to 0. Now x2 equal to 0 means that weight will remain 4 and value will remain 40. And then now let's apply greedy knapsack. So 4 is first item included, second item not included. So third item you can include all, and the fourth item you will include only 1 unit. So you get 40 plus 25 plus 4, which is 69. Okay, this is for the lower bound. For the upper bound, you have 4 and you're not going to include 7. So you can add 5 and then you can stop, because if you add 3 it will exceed, right? So you get minus 65 as the upper bound. Okay, and then so once you have done this, the minimum cost belongs to this node because it's minus 69, that is minus 57. So you expand this node. So now consider x3 equals to 1. When x3 equals to 1, the weight will increase to 9 and the value will increase to 65, right? And now let's find out the lower and upper bounds. So if you have included the first and the third item, then 9 units and then 1 unit you can add from here. So you get minus 69 as the lower bound using greedy knapsack, and then using just adding the items one after the other, 4 plus 5 9. You cannot add the entire 3 items more, so you just leave out the fourth item to get a maximum profit of minus 65. Okay, and now you can explore this one because it has the lowest cost, right? Minus 69, and that one is minus 57. So this one is lower, so you can explore it. So when you explore it, you can check out x4 equals to 1, and when you do x4 equals to 1, automatically the weight is exceeded, so you cannot explore it further. And then x4 equals to 0. When you do x4 equals to 0, you're basically saying that you're going to select only the first and third items. Even if you apply greedy knapsack, you get minus 65. And if you take the upper bound also, it's only minus 65. You cannot add any more items, okay, because weight will be exceeded. So here, this is actually a solution node which gives you the the profit as 65. And you see this node, see the upper bound here is minus 65. Optimal solution is minus 65, but the minimum here is minus 57, which is greater than 65, which means you can kill this because you want minimum value, right? You're not going to get a value less than minus 57, so you kill this. Okay. So now you can explore x3 equals to 0. So when you explore x3 equals to 0, you will get minus 52, minus 52. Again, this minus 52 is greater than minus 65, so this will also get killed. So now all the nodes have been explored, and so you see there is no other node to explore, so we get the optimal solution as minus 65. Okay, this is how branch and bound using for 0-1 knapsack problem works. And when are nodes killed? When you find a solution node with optimal value C, all other nodes with C cap greater than C are killed. Okay, so you found a solution node with some optimal value, and then when you do that, all other nodes with C cap greater than C, you can just kill them. Okay, so I hope you understood, and yeah, this is the end of the clip. Thank you very much.